All right. Well, if you think of anything, let me know. You might have already turned in your test, so you're done. But I just wanted to ask just in case. We are going to do something a little bit different. So we are actually kind of switching gears, and we're going to talk about probability, and so it's a little bit different. So something kind of fun and interesting. So the first thing that I want to talk to you about is something called the fundamental counting principle. Okay, so this is the idea. This is the fun picture that's right in the start of your screen that has the not straight line here, right, Anton? But if you think about how many choices there are for something, so you're going to go order pizza. And how many different ways can you order a pizza? Like how many different combinations of pizza can you get? Or you think about your outfit choices. So how many different ways with the clothes that you have can you come up with an outfit? And for a lot of those types of problems, we use something called the fundamental counting principle. So you can see it written right here. But the idea that if we have A ways of doing something and B ways of doing another thing, there are A times B ways of performing both actions. Okay, so that just sounds kind of like technical. So I feel like let's kind of do a fun example, right? So let's say that you're going to order some pizza, and we're going to make it really simple here. If you order a pizza, you get to choose the type of crust. You could either have thin or deep dish. And then you get to pick the toppings, which are pepperoni, bacon, or sausage. It's a pretty simple pizzeria, right? So how many combinations of pizzas can we come up with? Well, you have the choice of thin or deep dish, right? So there's two choices there. And then once you choose thin or deep dish, you have the choice of 3 different toppings for your pizza, right? So you could have a thin crust pepperoni, thin crust sausage, thin crust bacon, deep dish pepperoni, deep dish sausage, deep dish bacon, if I just said all that right. So those are your choices. Just the fact that you have 2 toppings and 2 types of crust and 3 toppings means you have 2 times 3 numbers of combinations. So you have 6 different pizzas that you could come up with. All right, so that's a really kind of simple example of that. But I think everybody can relate to that, right? Okay. So there are 2 times 3 equals 6 combinations of order pizza. So the fundamental counting principle is the number of ways in which a series of successive things can occur. So, for example, if you flip a coin and then you roll a dice, how many combinations are possible? So first we're going to, so I think these problems are fun because it's like, oh, something different, right? If you flip a coin, then roll a dice, how many combinations are possible? Okay, so first let's think about what we're doing. First, we're going to flip a coin. Here's my drawing of my coin here. Right? So when you flip your coin, how many possible outcomes are there of flipping a coin? You could have, 2, right? You can get heads or tails. Those are your 2 possibilities. So there's 2 possibilities when you flip your coin. Okay, so first you're going to do that. Then you're going to roll your dice. And we're just going to assume that it's a standard size dice, not like a crazy 20-sided dice. That would be crazy, right? So how many ways can you get it? Yeah, when you roll the dice, how many possible numbers can you get? 6, right? So when we roll our dice, we can get 6. So if we get 2, we could get heads or tails on the first flip of the coin, right? And then once we roll our dice, we have 6 combinations. So we would have 2 times 6 combinations. So there's 12 different combinations that we could come up with for when we flip a coin and roll a dice. Okay. Another way you could think about this, and I know it's kind of simple, but another way you can think about this is you can think about it like that tree that we were talking about. So for the coin, you could have heads or tails, right? And then next up, you're going to do your dice, which you can now call a die or a dice, I guess, when it's one. That's what I heard. I don't know if that's true or not. So when you roll your die, you could get 1, 2, 3, 4, 5, 6. And when you roll your die with tails, you could get 1, 2, 3, 4, 5, 6. So you kind of get this branch thing, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so then if you count up all those lines, that's your 12 combinations. One thing that you notice about this and this idea of the fundamental counting principle is that the second thing, rolling the dice, does not depend on the first thing. And we're going to talk about that as we get into the chapter, but they're each independent actions, right? You don't get certain numbers on your dice because you got heads or tails. Just like with the pizza, you don't, yikes. I don't know what that's about. You don't basically your pizza toppings don't depend on what kind of crust you get. I mean, maybe they do in real life, but your pizza combinations, don't worry, don't depend on that. Okay? Does that make sense? I think it's kind of fun. Okay. Next up. This one's fun for me. Let's see. All right, so who likes to wear like the same thing? Does anybody like to wear the same few items, or does anybody really like to like look at all of their closet and see all their choices? All right. We're gonna pretend like you've got your spring wardrobe, right? It's spring now. The weather's kind of changing. It's always tricky to figure out what you're gonna wear. All right. So this is the example. You're picking out an outfit. Okay. You have 5 different shirts that you can pick from. Okay, so you have 5 shirts you can pick from. You have 3 pairs of jeans and you have 2 pairs of shoes. How many outfits can you possibly make with your 5 shirts, 3 pairs of jeans, and 2 shoes? Okay, so this is not assuming any type of my I can't talk. My shirt has to match my shoes. I can't wear these shoes with these jeans. This is just how many outfits are possible. It doesn't matter if they look good or bad, right? So how many possible outfits can I come up with? So we're going to use the fundamental counting principle, right? There are 5 different possibilities for shirts, right? We have 3 different possibilities of jeans, and we have 2 different possibilities of shoes. And so if we multiply that all together, we end up with 30 possible outfit combinations. So again, the fundamental counting principle does not say that you're going to be selective. You know what I mean? What if one of your pairs of shoes was like red shoes? You have some red, one of your pairs is red, and one of your shirts is, what color wouldn't match? Pink. No offense if you wear pink shirt and red shoes, I'm all right with that. But let's say that they just don't clash. That's all right, Otto. Welcome back. That still counts as a combination, right? And so you're not like being picky based off of what shirt you pick. You're picking the jeans and the shoes. So let's see. Does anyone want to tell me, let's just kind of take off this because I think it's kind of interesting. Does anyone want to tell me in actuality how many pairs of how many different shirts you think you have? Just think of your winter shirts. How many winter shirts, like between sweatshirts and long sleeve shirts? How many? Anybody want to take a guess as to how many that they have? I'm guessing it's more than 5. You have 3, Otto? All right, he keeps it simple. I like it. That's actually okay. You just count your swim shirts and you have 25 perfectly around 5. Okay. So Otto and Anton are practicing it's like, is it called capsule, like capsule clothing, where you have like a limited number of choices, but then you actually have more choices than you think. All right, we're gonna go with Aaliyah since it's gonna be interesting. So she's got 25 different swim shirts that she could pick from in the morning. Okay. And Aaliyah, do you have any idea how many like pairs of jeans that you own? I probably own like 10, but I wear 2 of them. So 3. There you go. All right. So she's got 3 different pairs of jeans. And Aaliyah, do you have 2 different pairs of shoes that you wear or more? Like 4. Okay. Perfect. Thank you for sharing. Okay. So if Aaliyah wanted to come up with an outfit in the morning, she's trying to decide what to wear. How many different combinations does she have? So we would do 25 shirts times 3 pairs of pants times 4 pairs of shoes. So she has 300 different outfit combinations to wear. Combination. Right? So over 300. So you can see how, if you have a lot of shirts, like a lot of swim shirts from all your different meets, that all of a sudden you're going to have a lot of different options as to what you can wear. Somebody that really likes clothes that has like, 25 shirts and maybe 10 different pairs of pants and 10 different shoes, then you're talking 2,500 different outfit combinations. So no wonder some people take a long time to get dressed, right? And I'm just teasing because some people like to just enjoy it, right? Okay, so I think that's kind of fun. Fun and easy to understand, right? Let's do another example and talk about license plates. Okay. So in New York, so the license plate is on your car, right? A license plate is usually a combination of letters and numbers. In New York, license plates are all 3 letters followed by 4 numbers. Okay, so you get 3 letters followed by 4 numbers. And they get issued by the state of New York, and you have to wear it on your car. You have to put it on your car, and that identifies your car. So license plates have to be unique, right? Cannot repeat license plates. 2 different cars can't have the same license plate. Okay, so in New York, the pattern is 3 letters followed by 4 numbers. And Part A says, how many different license plates are possible if letters and digits or numbers can be repeated? Okay, so let's look at A, okay? And your license plate is going to be it's going to be a letter, and a letter, and then a number, a number, a number, and a number. Right? So we're going to end up with 7 different items. And items being letters or numbers on our license plate. That's what it's going to look like. Okay. We're going to say that we can repeat letters. So your license plate could be, AAA 1111. That would be a valid license plate. So we can repeat the letters and we can repeat the numbers. In fact, this would probably be the first one. So for something like this, physically counting them isn't going to be possible. So we're going to have to use the fundamental counting principle to think about what our options are, right? So the first thing is we're going to take the first letter. How many letters do we have in the alphabet? 26. There we go. Got 26 letters. Last I checked, Anton. Exactly. So for the first letter, we could have any letter from A to Z. So we got 26 letters, right? Then the next letter, could you repeat if you have, the first letter was B, could you repeat B again? Yeah, we're allowed to. We can repeat letters, right? So the next letter, we have 26 different letters to pick from. And then the third letter, we have 26 different letters to pick from. So already, just if we had a 3-letter license plate, we're going to have a ton of choices, right? Okay. But we also have a combination of 4 numbers. So numbers, what numbers could you have on a license plate? You could have any number from 0, 1, yeah, there you go, 0 through 9. So as Anton said, that's actually 10 different choices that you could have. So a lot of times people want to say 9, but both Aaliyah and Anton, you picked that up. You can have 0 as a choice, right? 0 through 9. So there's 10 different numbers that we could use for the first number. The second number we can do 10. The third we can do 10. And the fourth we can do 10. So what are we going to do? We're going to multiply all these together. And we find out that in New York, there is 175,760,000 different combinations of license plates. Right? That's a lot of different license plates that are out there. So you think of all the cars that you have and all the different things. All right. Does that make sense to everybody? Pretty straightforward, right? So then part B is, what happens if, how many different license plates are possible if letters and digits cannot be repeated? Okay. So same idea. We have a letter, a letter, a letter, then a number, a number, a number, and a number. So this is part B. All right. When we pick our first letter, we can pick any letter, right? We have 26 different letters to choose from. Okay. Or the computer, or however they generate that. When we go to pick our second letter, though, we don't have 26 choices because we can't repeat something. So we've already done a letter for the first one, right? So our second letter, there's only 25 different letters that we can choose from. So say B was our first letter, then we can't pick B for the second letter. So now we are down to 25 choices. And then our third letter, there's 2 letters that we can't choose from, so we only have 24 letters to pick from. Okay. And then our numbers, it's going to be something similar, right? We can't repeat our digits of our number. So the first number, we have all 10, 0 through 9 to pick from. And then our second number, we've already used up 1, so we only have 9 to choose from. Our next number, we have 8, and our next number, we have 7. Right? So if we multiply all those together, you end up getting, there you go, Otto, 78,642,000 different combinations of license plates. So by repeating letters and numbers in your license plate, you more than double the number of combinations that are available, right? More than double the number of combinations by letting repeating digits. So here's a question for you. I mean, at some point, if you made your license plates all numbers, So think about that, 7 numbers, right? At some point, adding one more number will give you more combinations, right? But you kind of get this diminishing return. So the idea of having both letters and numbers on a license plate actually allows you for a lot more choices because you're getting the most choices out, especially if you want to not repeat numbers. And then there's probably some subtracted out there because, you know, they can't be a valid license plate or they're whatever they might be. So that is license plates. There's also a problem in your book that it is, I don't think I have it. Oh no, we do have it. Okay, so that's the fundamental counting principle. Everybody feel kind of comfortable with that? Cool. Where? All right. There we go. Cool. All right. So, but wait, there's more. So that's the fundamental counting principle. That means that it's basically what you choose each time doesn't depend on the order in which you pick them out, right? So like it didn't say on your license plate, if you pick an A, then you can, if you pick a C, then the letter after that can only be something from D to Z. You know, it can only be a letter afterwards. It's kind of this idea of, I don't want to say completely random, but there's not a dependency between what you're choosing. There was a little bit of a dependency in this last problem we did because you couldn't pick the last letter, but it's really just narrowing the pool of what you can pick. It's not really saying like, oh, if you picked an A, then your next number has to be a vowel. You know, there's no like dependency like that. So there's actually more in 10.1. 10.1 is kind of packed in there. And so that's your next page in your notes. And it is what happens when the order in which we pick things matter. Okay. So when the order matters of how we pick things, then we use something called a permutation. Okay. So I try to remember the word permutation by permutation picky. Get that P. Permutations when we're picky. Okay. So there are 3 types of permutations, and we'll talk about what these are, but I just want to kind of put that out there. So one is that if you have the number of permutations of n objects that and repetition is not allowed, you use n factorial. And actually, let's just kind of leave it right there. I'll talk about the rest of these later. Okay, so let's talk about if we're worried about the order in which we pick things, we're using permutations. And I just told you when we have the number of permutation of an objects and you can't repeat, it's n factorial. So who has seen the factorial before? Or as some of my students like to say, n, right? Who's seen the exclamation point before? Or who's this new for? Or you've seen it, but you don't quite remember? All right. Well, I'm gonna take that as let's do a little, yeah, somewhere in there, right? All right. So the factorial symbol is written like an exclamation mark. So you might see something like 6 factorial or 10 factorial or 100 factorial. That would be a really big number. And so it's called a factorial. It looks like an exclamation point. And basically, it is you take the number that is in front of the factorial and you're going to multiply that number times one number one less, times one less, times one less, all the way till you get to 1. So you can see right there, 3 factorial is 3 times 2 times 1. If you had 4 factorial, that would be 4 times 3 times 2 times 1. Okay, 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, if you had, I'm not going to write this out, if you had 100 factorial, it's going to be 100 times 99 times 98, all the way down till you get to 3, 2, 1. Right? So this idea of factorial, you can maybe see how would be helpful just taken from that last license plate problem, right? If I wanted to know how, if I want to write a license plate that's 26 letters long, which is not going to be true, but like I wanted to pick out I could pick one letter from the alphabet and then my next letter couldn't be any of the ones I used before, but I wanted to basically pick all the letters of the alphabet and write them out in a random order. I would do something like 26 factorial. It's not the perfect example, but you can kind of see in that last license plate example how we ended up doing 26 times 25 times 24. And we stopped there because we only needed 3 letters. But that idea of factorial as a way of simplifying when you're multiplying sequentially smaller numbers. Okay. The good news is that they're pretty easy to work with. And there is most of your scientific calculators should have a factorial button on them. So on your TI, it is under, I always forget where. Okay, it's under a math, and under math, there's a menu that says PRB for probability, stands for probability, and the 4th number down is an exclamation point factorial. So it's under math, and then the menu over to the right that says PRB, which stands for probability, and then in mine it's number 4. There's a factorial button. Okay. Desmos also should have this. Don't have Desmos up, but it also should be under probability in Desmos. So if you do 6, I don't even know if you type on your keyboard. Nope. What did I do? Oh, okay. So you could just type it in like keyboard wise. You could also do 6 functions. Oh, it does not have it in there. So I guess you just have to type it in with your keyboard. I would have thought it had it in there. While I'm in here, we are going to be talking about a couple things with, and this isn't going to make sense right this second, but we're going to be talking about NPR and NCR. I don't know if we'll get to those today, but that's under your stats button. So those are in Desmos as well. So I just want to show you they're there. So 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1, right? That's what that represents. So you can probably imagine that factorials get really big really fast, right? So if you do 10 factorial, you're already up to 3,628,800. If you do 100 factorial, you're at a gigantic number, right? Because you're just multiplying by the next, you're just exponentially growing your number. Actually, that would be interesting. What if we did y equals x factorial? Okay, so kind of ignore this side of the graph because we're not going to use it for negative numbers, right? But look what happens if I just kind of ignore that, right? So if you have 0 factorial, that's one thing, but you have 1 factorial is 1, right? 2 factorial, if I can get there, is 2. 3 factorial should be 6, if I can get there. 3 factorial, 6. And then what happens to your curve? It just exponentially grows, right? By the time you get to 5 factorial, you're like way up here. So your factorials just kind of goes crazy exponentially. Okay, side note about factorials. I promise that we're not just randomly talking about them. It is a cool graph, Anton, I agree. I've never actually thought to graph that before, but I don't even know what's happening with a negative factorial. I think it's kind of not so happy that we're doing a negative factorial. And really, when you talk about factorials, you don't really do them with decimals. Like it's really just an integer thing that you use factorials for. So this is interesting. Interesting and artistic at the same time. Okay, so I'm just thinking how I want to tell you this next. All right, so let's pretend that you are going to I'm just trying to think of a fun example. You're going to write the word wow. You're going to write the word wow on your paper, and you have a red marker, and you have a blue marker, and you have a yellow marker. Okay? And I want you to write the word wow using red, blue, and yellow, but you cannot repeat the colors. Right? You cannot repeat the colors. So what that means is, if you write the first W red, then your only 2 choices for the second ones are blue, then yellow. Or if you write the first one red, then you could get, I'm doing that mind trick where you're you're writing the colors and the letters at the same time. I'm like playing my own psychology here. Do you guys know what I'm talking about? Like if you see the color and the letter at the same time. Yeah, like if you wrote this, see, I'm doing it wrong. If I wrote this, in your brain, what do you read this as? Blue or red? Sorry, slightly off topic, but that's like a psychology thing, like when you're trying to read a word that's written in the other color. So I just did that to myself. Okay, so back to the example. I'm writing the word wow. The first letter I write is red. Then I could write blue, then yellow, right? Or if the first letter I write is red, I could write yellow, then blue, right? And so then I can go on from there. So mathematically, there are 3 ways to pick the first color, right? I have 3 different ways. This first W could be red, it could be blue, or it could be yellow. So there's 3 choices that I have for the first color. For the O of wow, right? I've already picked a color for the first one. So for this one, there's only 2 choices that I have left, right? And then for the third letter, I've already picked the first 2, so there's only 1 choice that I have left. So in this case, it's 3 times 2 times 1. There's 6 different ways that I could write the word wow, right? So there's 3 choices. 3 factorial is also 6. Okay. So let's make it a little bit fancier though. What if I wanted to write the word, let's see. Trying to think of a 5-letter word. Tell me a 5-letter word that I can write on here. Oh, we'll go with a 6-letter word. Spring. Spring. Okay. I want to write the word spring. I'm like into lettering and making cool text and letters, right? I'm trying to write the word spring, and I have 6 different shades that I can use. I have a blue, I have a yellow, I have a red, I have a green, I've got a pastel pink, and I have what color did I not do? An orange. Okay. Got an orange. Okay. So I'm going to write this spring, the word spring, super fancy. So, one example would be like, I'm going to write my fancy letters on my computer screen. This is totally not fancy. ING. That's my fancy lettering. Aren't you guys proud of me? All right. So that's one example of how I could write the word spring, right? But I have 6 letters, 6 things that I'm going to do, but I'm not going to repeat any colors because I just don't think that'll look good. If I write the word spring with, 2 blue letters, not going to look good. So how many different ways could I write the word spring? Right? So when I go to write the first letter, I get to pick any of my 6 letters. So there's 6 different choices, right? Then when I get to my P, I've already used one of my color choices, so I'm down to 5. When I get to the R, I've already used 2, so I only have 4 choices left. When I get to the 4th letter, I've already used 3, so I have 3 remaining choices. When I get to the 5th letter, I've used 1, 2, 3, 4, so I only have 2 left, and when I get to the last letter, there's just 1 letter left. Right? So I can multiply those all together, and it's the basis of that is the fundamental counting principle, right? We're not repeating anything over and over again. So another way that I could write the number of choices is 6 factorial, which is what we happen to do in Desmos. So if you multiply these together or you do 6 factorial, there are 720 different ways to write the word spring with 6 pencils, right? So that's one way that we use permutations. Okay. I'm going to show you the next way, and then I think we're not even going to finish this whole. I don't even think we're going to finish today, but I do want to kind of give you a preview for what the other way it is. Okay. Okay. So the second thing here says that if you want to find the number of permutations, so the number of possibilities basically, of R objects taken from N objects, and repetition is not allowed, we do N factorial over N minus R factorial. So whenever I first see this, it feels like Greek. It's like, what? Huh? But it actually makes sense once you kind of break it down. So let's say that you have, this is from your notes. Let's say you have 15 of your favorite songs. These are your These are your favorite songs. These are the ones that you go to when you like, you know, just want to whatever, zone out, listen to music. So 15 of your favorite songs, right? But you are going on a little or you're getting ready to go to, I don't know. You're getting to get ready to go to some fun activity and you only have time to listen to, let's say, 6 of those songs. So that's about, you have like 20 minutes. You have time to listen to 6 songs, right? You have 15 that are your favorite, but you really can only have time to listen to 6 songs. You need to pick from your 15 songs, 6 of them to play before you go, I don't know, somewhere fun that you're excited to go to. Okay. So how many ways can you pick 6 songs from your 15 favorite songs? How many combinations are there? And do you want to repeat songs on your playlist? If you only get to listen to 6 of them, do you want to repeat the songs? No, right? You don't want to repeat the songs. You want 6 unique songs. You want them each to be different. Okay. So that's where this idea of the number of objects taken from objects with repetition not allowed. So we have our objects so we have 6 songs that we're taking from 15 different choices. Okay. So what we're going to do is we're going to use this formula. Right. So in this case, we have n different songs. We have n, which is 15 different songs to choose from, but we only get to pick 6 of them. So in order to find how many different combinations of 6 songs that we can have that are picked out of 15, we're going to do n factorial divided by n minus r factorial. Okay, so we have 15 factorial divided by 15 minus 6 factorial. Okay, so this is the same. You could also write this as 15 factorial over 9 factorial if you wanted. Okay, so if you evaluate that, does anyone have any idea, if you're not looking at your paper, how many different choices you would have? You have 15 songs and you pick 6 of them. We would have 3,603,600 different playlists that you could come up with 15 different songs. So if if any of you are big music fans, I'm sure that you have way more than 15 favorite songs. Or say you have like music loaded onto your phone or iPod or whatever you listen to, right? Say you have 100 songs that you like to listen to. Like, what are the chances? Yes. Yep. Different order. Thank you, Anton. But I mean, think of how many different ways that music can come up. And in your head, sometimes I feel like always the same playlist comes up, but there's so many different ways that those songs could come up. And Anton, you made a great point that it's different order, right? Can't repeat the songs and they would be, so technically if you, if you played song A, B, and C, playing song C, B, and A would be a different combination. Okay. All right. So what are you kind of doing with this formula? So remember, if you just wanted to know if you had your 15 songs, right? And you were going to play all 15, how many different ways could those be ordered ordered when you're not repeating them. That would just be 15 factorial, right? You're just playing all 15 songs and different orders. So that's 15 factorial. So what this is doing is it's taking that 15 factorial, right? And it's dividing out because you're only choosing 6 of those songs. So you're taking out part of the combination. So playing your 15 different songs in any order would be a much higher number of possible combinations versus just playing 6 out of your 15 songs. Okay. I'm going to do one more last thing with this. This formula is a powerful formula in probability, the idea of picking the number of items out of a group of items, so in combination. And so remember just in Desmos a few minutes ago when I told you that NPR would be important? This idea of n factorial over n minus r factorial actually can be written as NPR. Okay, so you have the number of items total picked by R objects, NPR. So I'm not explaining this super well, but let me just show you because I think it makes more sense when you see it. Okay, so we just said that we had, 15 songs, which 15 songs could be played in all combinations, right? And then we are only picking 6 of those songs, so it's 15 minus 6. So that's how we end up with our 3,603,600, right? So because this idea of picking items that cannot be repeated out of a larger group is something that's used so much in math, there is a function, which is this NPR function. So, and your calculator works a little bit different too. Your TI works a little bit different, but it is also under there, under math probability. There's this NPR button. But what we do is we say that we have n number of items, so we have 15 items, and we're choosing 6 of them out of that items. So you can see that it ends up calculating the same number. So because this idea of picking another number of objects is so important, there is a mathematical function that is recognized NPR, and there's one NCR as well that that represents that. The P stands for permutations. The C, which is in 10.2, stands for combinations. Okay, so that's kind of the difference between the two. So we're not even quite done with 10.1. There's just a lot in this section, but I think you should be able to get started on the questions that have to do with fundamental counting principle and some of the first problems. We did not talk about, what we didn't talk about yet was, and feel free to read it if you want to get ahead. If you are picking, you have 15 songs, and you're okay with repeating your songs on your playlist. Ugh, we don't like that, right? No, there's other examples where we want to repeat. So this formula actually deals with you're picking the objects and that one of the objects is repeated. But we will talk about that on Monday. All right. So hopefully that all made sense. We'll talk more on Monday. We'll go over it more Monday. But I appreciate you guys coming today, and I will see you on Monday. All right. Thanks, guys.